Alright, in this video, the last video of 11th week, we are going to study how to find the relative max or mean when function has multivariables. Okay? So I'm going to illustrate that by going through several examples. Okay? And procedure is as follows. So now we are going to find the relative max or mean based on the theory we discussed in the previous video. So the first step of identifying relative max or mean is we start with partial derivatives. Okay? Remember the first of the condition. The two partial derivatives or three partials, depending on the number of variables, we have to set them equal to zero. Okay? So in case of two variables, we compute two partial derivatives and set them equal to zero. Okay? And that gives me simultaneous equations, right? And by solving these simultaneous equations, we can find the critical points of multivariate function. Okay? And the third step is we compute all second partial derivatives and then construct the Hessian matrix. This Hessian matrix, compute f of xx, f of xy. We don't have to compute the f of yx. That is going to be always the same as f of xy. Okay? So we have to compute three second partial derivatives. Okay? And then construct this Hessian matrix. Okay? And then determine whether Hessian matrix is a positive definite or negative definite at the critical points we found at the second stage. Okay? And then depending on whether that is a positive or negative, we can classify whether the given critical point, so at the given critical point, the function attains max or min. Okay? So let me start with this example. Right? So find all extreme values of this function. So once again, the first step is we start with the first order partial derivative. Okay? So call this function f of x and y. Okay? And what is f of x? That is a 24x squared. Okay? So, and then the second term gives me 2y. And the third term, negative 6x. And the fourth term, 0, because y is a constant. 1 is originally constant, so it's going to be 0. Okay? And f sub y, okay? This guy, constant. The second term, 2x. The third term, constant, so it goes away. Fourth one, 2y. And then 1, that is a constant. Okay? So we just computed first order partial derivatives and set them equal to 0. Okay? That gives me simultaneous equations. We have a pair of equations for x and y. Okay? And then, unfortunately, we can apply the matrices because, the first equation, this is a non-linear equation. We have x squared. Yeah? So we can apply the matrix algebra, but if we take a look at the second equation, 2x plus 2y is equal to 0. Okay? So that means now the second stage is solve this equation to find critical points. So from the second equation, we know x is minus y, right? So I can plug in negative y for x in the first equation. Then 24x squared becomes 24y squared and 2y. And minus 6 instead of x, I can put in negative y. Okay? So rearranging the left-hand side, so 24y squared plus 8y, that is 0. Okay? So factoring out 8y, and I will be left with 3y plus 1. Okay? So we have two solutions. Y is 0 or negative 1/3. Okay? And because x is a negative y, so when y is equal to 0, corresponding x is 0, and the corresponding x to negative 1/3 is 1/3. Okay? So we have two critical points. We identify two critical points at the origin, 0, 0, and at 1/3 and negative 1/3. Okay, so that is a second step. And the third step is now we compute second partial derivatives to construct the Hessian matrix. Okay? So we know f sub x is right here. So we know the expression of f sub x. So from this, I can compute f sub xx. Okay? So this guy, variable, so whose derivative is 48x, 2y, constant, negative 6x, variable, whose derivative is negative 6. Okay? Then f sub xy. Now given this function, okay, we take the partial with respect to y. So now 24x squared, constant, 2y, variable, that is 2, whose derivative is 2. And finally, negative 6x, that is a constant. Okay? So f sub xy is equal to 2. And by Young's theorem, we know that f sub yx is also 2. Okay? And then finally, f sub yy. Okay? So f sub y is right here, 2x plus 2y. And we regard y as a variable, x as a constant. Taking derivative, we obtain 2. Okay? So the Hessian matrix H is f sub xx, f sub xy, f sub yx, f sub yy. Okay? So now we put in these values. 38x minus 6, 2, 2, 2. Okay? So this 2 by 2 matrix is going to be Hessian matrix in this example. Okay? Now we determine whether this guy is a positive or negative definite. Okay? At 0, 0, at the first critical point, the Hessian matrix is going to be because 48x is going to be 0 at this point. Okay? So this is going to be Hessian matrix at this point, at the first critical point. Okay? So this smattering matrix, so now we determine whether this is a positive or negative definite. So the first leading principle is negative 6, so H1. So the first leading principal minor, that is a negative. And the second, so I can take the determinant parenthesis, H2 is negative 6 times 2 minus 4. So that is a negative number, right? So going back to the characterization result. So we have two negative signs. It falls in this case. Okay. So we conclude that at the first critical point, Hessian matrix is indefinite. Okay, meaning that we can't tell whether so at this point the function does not achieve extreme value, extremum. Okay, because when given matrix is indefinite, that means the sign of the quadratic form, so the sign of d squared z is undetermined. So it can be positive or negative depending on dx and dy. In this case, in most cases, when Hessian matrix is undetermined, we are gonna have a saddle point. Okay, but I think it's enough to answer that at this point, the function does not achieve extreme value. Okay, so we may have a saddle point or inflection point. It depends on the exact functional form, but we are not interested in the non-optimal values. We are only interested in optimal values. Okay, so now we examine the second critical point. At the second critical point, 1/3 and negative 1/3. The original Hessian matrix was 38 x minus 6. Okay, so now I can put in 1/3 for x here. Okay, then Hessian matrix becomes we can evaluate Hessian matrix at the second critical point. Then I obtain 38 divided by 3, that is 16. 16 minus 6, that is 10. And 2, 2, 2. Okay, so now the first leading principal minor, that is 10, positive. And the second is a 20 minus 4, 16. That is a positive. So all leading principal minors turn out to be positive. It means the Hessian matrix is a positive definite. Okay? When Hessian matrix is a positive definite, we have a local minimum at that point. Okay? So we have a local minimum. So the function attains a local min at 1/3 and negative 1/3. Okay, and the local minimum value, you can put in 1/3 for x and negative 1/3 for y. You can identify, you can evaluate the function at this point. Okay, so that is it's just a simple computation. So let me skip that. Right, in the second example, we have some function involving exponential function. Okay, does not matter. We can follow the same procedure. So all right, so I think there's some error with my camera. I just fixed it. And let me call this function, say g of x and y. Yeah, let me stick to f to avoid any confusion. So call this function f. Okay? Then f sub x, that is 1 minus e to the power negative x. Okay? X becomes 1. 2e, remember e is a number, irrational number. 2ey, that is a constant. So that goes away. And negative 2x, or e to the power x, so e to the power x's derivative is itself. Okay, so we just have e to the power x. Negative e to the power 2y, because y is a constant. So that also goes away. Okay, so we have these two terms. F sub y, okay, x is a constant. 2ey becomes 2e, okay? And e to the x constant. And e to the power 2y, okay, e to the power 2y's derivative is, we rewrite this function and then multiply by derivative of the power, that is 2. Okay? So 2 e to the power 2y. Okay? And set them equal to 0, the first order condition. Two partial derivatives must be equal to 0. Okay, then we have to solve this equation. Okay, the first equation says e to the power x is equal to 0. When does natural exponential function take the value of 1? When x is equal to 0. Okay? You can solve this equation by taking natural logarithm. So ln e to the power x equals ln 1, but ln 1 is always 0. ln and e cancelled, so we have x is equal to 0. Yeah? So when x is equal to 0, no matter what the base, we have always 1. Okay? And that is a unique solution to this equation. Okay? The natural exponential function takes value 1 at the unique place, at the unique point when x is equal to 0. Okay? So the first equation, from the first equation, we can find the value of x. Okay? And from the second, 2e equals 2 e to the power 2y. So canceling off 2 first. Okay. So we have e to the power 1 on the left and e to the power 2y on the right. Okay. So in order to make these two equal to each other, 2y must be 1. So y should be 1 half. Okay. So this function, the given function, has a unique critical point at 0, 1, 2. So we have a unique critical point that occurs at 0, 1 half. Okay. So now the third step is we have to compute all second partial derivatives and then construct a Hessian matrix. Okay. So we start from f sub x. So from that, I can compute f sub xx. So one constant goes away, negative e to the power x. There is a negative e to the power x. Does not change at all. Okay? F sub xy. There is a no y here, right? But when we compute f sub xy, y is the only variable, but there's no y here. Everything is a constant. So derivative is going to be 0. Right? So f sub yx is also equal to 0. That follows from Young's theorem. And then f sub yy. Yeah. From that, I can compute f sub yy. 2e constant. And 2e to the power 2y. So that becomes negative 4. Okay, once again. I have negative 2. So leave it alone. And then e to the power 2y's derivative is 2 e to the 2y. So e to the 2y times 2. So negative 4 e to the power 2y. Okay, so Hessian matrix is going to be I think I need more space. So negative e to the x, that is f sub xx, f sub xy is 0, f sub yx is 0, and f sub yy is negative 4 e to the power 2y. Okay? So at the unique critical point, now we determine whether this matrix is positive or negatively definite. So we first plug in 0 for x. So the given function has a unique critical point. Okay? So we have to determine this guy is positive or negative definite at this point. So we first evaluate the Hessian matrix at the given critical point. So e to the x is going to be at 0, is going to be negative, it's going to be 1. This guy is going to be 1. And when y equals 1 half, this guy goes down to negative 4, e to the power 1. Okay, so negative 4e, number e. Okay, so the first leading principle, minor. So the first principle minor is negative 1, that is negative. Second, negative 1 times negative 4e, and we have 0 off diagonal. So for E, 4 times E is going to be second principal minor. That is a positive. The sign starts from negative and then it alternates. So we conclude that this matrix is negative definite, meaning that D squared Z is always negative. So according to the differential version of an optimization test, we conclude that the given function attains a local maximum at this critical point. So obtains local max at 0, 1 half. When x is equal to 0 and y is 1 half, so e minus 1 minus e. So the local maximum value is negative 1. If you evaluate this function at this point, you're going to get negative 1, I guess. All right, and then let me do just one more example. Okay, the third one. Now the function depends on 3 variables. x1, we have x1 and x2 and x3. Okay, so let me call this function f x1, x2, x3. Okay, procedure is the same. We start with first order partial derivatives. So f sub 1. Let me call the f sub 1 the partial derivative with respect to x1, the first variable. Okay, then 2x1 becomes 4x, 4x1. x1 times x2 becomes x2. Okay, for x2 squared constant, x1, x3 becomes x3, and the other two terms are constant. Okay? So we have this f sub 2 partial derivative with respect to x2. Okay, so now regarding x2 as the unique variable, regarding x1 and x3 as constants. x1 constants, x1, x2 becomes x1, and the third one becomes 8 times x2, and x1 times x3, x2 is a unique variable, but this is a constant. Constant, constant. So we have this. f sub 3, finally, constant, constant, constant. x1, x3 becomes x1. x3 squared 2x3. Okay, and 2 is a constant. Okay, and then we set them equal to 0, 0, 0, 0. Okay, that it comes up with linear equations. Okay, system of 3 linear equations. So you can solve for x1 and 2, 3 using matrix algebra, or so if you express that in matrix form, 4, 1, 1, 1, 8, 0, 1, 0, 2, x1, x2, x3, and we have a 0 vector and 0 matrix on the right. Okay, so this is a homogeneous equation system, and you can easily check this matrix is invertible. Okay, meaning that this equation has a unique solution when x1, 2, 3 are equal to 0. Okay, so the unique solution to this equation is x1, x2, x3 equal to 0. Okay? Because this coefficient matrix is invertible. Okay? Determinant of this matrix is non-zero number. Okay? I leave it for exercise. Okay? So that means the function has a unique critical point. Unique critical point at 0, 0, 0. All right? Cool. And we compute second partial derivatives. Okay. Once again, because the function depends on three variables, and we have a 3 squared, so total 9 second partial derivatives. Okay, but the first order is a linear, so it's not that difficult to find all partial derivatives. F sub 1 1. Okay, so we start from this one. X1 is the only variable. 2, 3 are constants. And F sub 1 1 is going to be 4. And F sub 1 2. Now X2 is a unique variable. That is 1. F sub 1 3. Now X3 is the only variable. That is 1.